All right, here we are with video 3 in a series going over question 3 of version J of the AP Physics 1 2026 free response questions. Question 3 is the experimental design and lab applications. I think we usually abbreviate this as the lab question, but this is the one where you're going to design a lab and do some linearizing with a graph. Now, for AP1, it looks a little bit different than it will for APC mechanics. Again, hopefully these videos are useful for all of them. I'll talk about some of the differences between those two as we go over this. Please remember that these videos are intended both to recap the recently released AP questions for AP1, but also help any students that are studying for maybe future exams or even the APC equivalents of these, where it'd be a little bit tougher, but the same type of skills are expected. In fact, all these skills are kind of the core ones that are expected for all of the physics exams, be it AP1, AP2, APC Mechanics, and APC E&M. All of these core ideas are applied just with different material. As a side note, if you're watching this video first, I have also put together, this is only, I think, a couple of days after the questions have been released, I went to the trouble of writing up what I think is a good guess as to what the grading rubric would look like. So not only the correct answers, what I'm pretty certain are the correct answers, but also a breakdown of how you would get partial credit. So if you're watching this shortly after having taken the exam, hopefully this may give you insight that if you're like, oh man, I bombed that test, but then you look through this and go, oh, I think I got a lot of partial credit on there. You don't always have to get the correct answer in order to get a good score on the AP Physics exam, especially in the free response because, well, I guess multiple choice, you'd have to get the correct answers. But for free response, we're looking for you to demonstrate the things that you know. All right, now that we've got that primer out of the way. Also, in case I forgot to mention it, I'll try and link down in the comments for this video so that you can access the grading rubric and probably the questions themselves. They're easy enough. You can find them on the AP website. Okay, now that we've got that. Question 3. I am so conflicted about question 3. I saw feedback from different students, including my own, that were saying, oh man, that was a really terribly tough question. It both is and yet it isn't. So this is the second year that we have of the redesign and realignment of the AP Physics 1 material, but you can actually see hints of this as you go further back. I think 2 or 3 years ago, there was a lab question about having known masses, a spring, and you were trying to find the spring constant, but the only piece of equipment you had was a stopwatch. They're starting to do this to get a little creative with it. I both really like this and hate it at the same time. The way that I describe this is basically whoever wrote this question, or College Board more broadly, this could be phrased as, I'm thinking of a lab between 1 and 100. What number am I thinking of? Like, this is, I can only think of one answer to this. That doesn't mean that there aren't more answers, but I'm pretty certain I know exactly what lab they're wanting us to do, but it takes a little bit to actually work your way to it. I'm going to walk you through some of the derivation stuff with this too, so that hopefully you'll have a good understanding of exactly what I think was expected of you all for this question. But we'll also talk about what you actually need to do in order to get either some of the points or all of the points. Okay. A group of students are investigating friction using the following procedure. The students release a block of unknown mass. I'm going to come back to this because I think it would have been better if they said that this was a known mass, but we'll talk about why. They do identify this as an unknown mass near the top of a curved ramp. The block slides down the ramp. The block then transitions to a horizontal surface as shown in figure 1. Frictional forces are negligible between the block and the curved ramp, but there is friction between the block and the horizontal surface. Okay, I read all of that. Hopefully my brain hasn't melted completely yet, but I've been in a room talking to myself for like an hour now. Anyway, back on topic. The ramp is frictionless. We got the block sliding down the ramp, and then when it hits the ground, we got friction on the ground. Okay, the students are asked to perform an experiment in which a single quantity is varied in order to collect data that could be graphed to determine the value of mu sub k, the coefficient of kinetic friction between the block and the horizontal surface. The students have access to only a meter stick. Budget cuts. All right, so we have to get creative on this. This can be a really tough one. So first, let me say the following. I'm still getting used to, and we haven't seen as many of the grading rubrics that have come out yet. If you get to a point where you're designing a lab and they're telling you that you have limited equipment, If you run into a wall and you can't actually come up with a working lab based on that limited equipment, go ahead and write a lab off of using additional equipment. Now, you're not going to get full credit, but you can get some partial credit as we go through. I'm hoping this advice proves to be good long term, but this is only the second year that we've seen this. And last year's experiment was a bit different where they didn't limit your equipment. I've only seen this a couple of times, and the last time that we saw it was before they did the realignment, when the experimental design questions were much tougher and much more detailed. Like, this is tough, but you can get a lot of credit in a different way than it used to be. It used to be just more tedious. Okay. So worst case scenario, I would recommend to my students that if you can't think of, if they're limiting equipment, if you can't think of how to do it with just a meter stick, go ahead and give me a good procedure to get the job done using other equipment. But understand that you're probably not getting full credit, but you can still get partial credit depending on how you set it up. Okay, now that we've got that, let's talk about how we can actually work with this. One of the things that I've told my students multiple times, and I'll remind everyone of now, is energy is an incredibly powerful tool. If you can solve a problem with energy, do it. Some of the big limitations for energy are going to be they cannot tell you direction because they are scalar, and they cannot tell you the time. But on this, we don't have access to a stopwatch, so maybe that's actually a really good thing. And on top of that, the main thing that I can change is, well, I got a ramp here, I could change where I let go of the block on it. Okay, well, that would allow me to measure a vertical height using my meter stick from the ground here. That would give me an idea of gravitational potential energy. And maybe I could look at what happens to that energy as it goes forward. Here's the thinking that I ended up going through. Now, you might be tempted to do something with kinematics, but with kinematics, yes, you could measure a distance, but you don't have a reasonable way that I can think of to measure velocities. You have no way to measure time because we don't have a stopwatch. You also don't necessarily know the acceleration. In this, they were also careful to make it a curved ramp, not a straight inclined plane. If it were a straight inclined plane, if we knew the angle, then we'd be able to do a lot more with it, as we will see in the second part of this question. That being said, there are a lot of clues on this that energy is really the best way to go about this. Now, if you don't catch that, that can be rough. That can set you back some, and maybe you're not going to get full credit, but you can still get partial credit by going through and designing things around the way that you can. But we have a few clues in here that energy might be the best way of going about it. So let's think about this with energy. I'm going to take my block, I'm going to put it up on the ramp, and I'm going to hold it here, and I want to think about the energy. What does my energy look like at the very beginning? Okay, so this is the part that you don't actually physically have to do on the exam in order to get credit, but if you're actually answering this correctly, either you're guessing, or you kind of have to do this to get an idea of how to work with it. Okay, so here's what I'm going to do. I got my ramp here, and then I got my squiggly ground here. I got two spots. I got here, I'm going to call this A, and then I let go of it, it speeds up, goes down here, and then eventually comes to a stop here at B. Okay, at point A, my energy at point A. Well, I'm holding it there at rest, presumably, which would be a good thing to do because I have no way to measure the speed. So I would have my kinetic energy is 0 plus mgh, where I could measure my vertical height here, h. Great. That's something that I can measure with my meter stick. Okay, next, now that I've got that energy at the beginning, that's all my energy at the beginning. It is all in gravitational potential energy, and it needs to be equal to, well, I would do equal to, except what's my energy at the end? Let me backtrack. Now that I'm thinking about energy, while we usually conserve energy, I would conserve energy all along the frictionless ramp, but as soon as I hit the friction, I'm actually going to end up losing energy. My energy at point B is going to be 0. I'm now at flat table, which is my reference height, and I'm also not moving if I go to the very end. I'm going to say that it slides a distance d. Okay, so with this, with my energy at point B, I have 0, just straight up 0. I started with mgh, and then I ended with 0. Where did that energy go? Well, friction took my energy. And how do we how do we remove energy or add energy? That is the work. The work done by friction, which is the only work being done on this system, would be equal to our final energy, 0, minus our initial energy, which is mgh. Here's a statement of work energy. Okay, great. Now that I've got this, I can take this a step further. My work equation tells me that work is done by taking the force of friction times the displacement. I'm going to fill this in that I could measure from the base of the ramp how far this thing slides. I could call that the sliding distance. Once again, something that can be measured with a meter stick. And I can set that equal to 0 minus mgh. Oh, technically, cosine of the angle between them. So in this case, with the cosine of the angle between them, when the block is sliding, it is moving to the positive x direction, or to the right. The force of friction would oppose that to the left, so we would have an angle of 180 between them. Cosine of 180 is -1. Basically what we get is negative force of friction times our slide distance is going to be equal to negative mgh. This cancels out our negatives. You can also come to that conclusion by saying, I start with mgh, and then I lose all of that energy. Friction had to take it, so the work done by friction is that. Now, I'm kind of going in a different way than might be best to kind of come up with this on your own, but I did want to do the derivation. Our force of friction is something that we have a good idea that we need to incorporate. I probably should have started with this, because we are looking for mu k. Okay, whenever you're looking for something, you should always look at what equations contain it. There's only one equation that has that. Our force of friction is equal to our coefficient of kinetic friction times our normal force. When you have the block on flat level ground, we have the force of gravity down, mg, and we've got the normal force up, so our force of friction will be equal to mu sub k times mg. Now, in this case, if I go back just a step, I had the force of friction times my stopping distance is equal to mgh. G we know because that's a constant, like unless they tell you otherwise, assume everything's on Earth, that's 10. H is something that we can measure with our meter stick, and D is something we can measure with our meter stick, but here's why I said that unknown mass kind of irritates me on this, because I could see a lot of students getting to this point going, well, this is a dead end because I can't find the mass with just a meter stick. Maybe if I sat and thought for a long time, I might be able to come up with a creative way to do that, but I probably need additional equipment. This is why I think I would have written this, that it is a known mass, so that if you got this far through, you wouldn't go, well, this is a dead end because I don't know mass. In this case, unknown mass still applies because I can replace the force of friction with its equation, mu sub k, mg d equals mgh. Here's my force of friction times its displacement that it's applied over, and that will be equal to the total energy that I started off with. I can divide both sides by mg. That's what gets rid of my mass. It also gets rid of g. It doesn't actually matter if you do this on a different planet. And we end up with the following. Here's your actual equation. Mu sub k d equals h. The two things that you measure in order to try and get this set up are your vertical starting height and your horizontal stopping distance, measured from the base of the ramp, the end of the frictionless part of the ramp, to where the block stops moving. You might measure from the front of the block if the size of the block is important, that sort of thing. In this case, the next thing that they're going to ask us to do, this is how I would go through and actually plan it out. I would kind of work my way through, do the derivation, and here's where I can go, okay, the things I need to measure are D and H, and with them, I can solve for mu k. On top of that, because this is a thing that they seem to be doing across all the exams as well, in part B, they said allow them to determine mu sub k using a linear graph. So reinforcing. In my class, we go through the following with linear graphs. You're going to see this in the next part. We have y, what's on the vertical axis, x, what's on the horizontal axis, and we've got our straight slope here. So we end up with y equals mx. With this, if I rearrange this, I can put h equals, I want my slope to be the thing I'm looking for, mu sub k d. All I've taken is mu sub k d down here, h down here, and we can see that this is how I would make my line. So what do I need to graph? I want to generate a graph of vertical release height as a function of slide distance. And the slope of that line, or that straight line, will be my coefficient of friction. Kinetic friction in this case. Here's me planning it out. Now that I've done that, I can go through and actually write this up as an experiment. The two things that I need to record are the vertical release height and the horizontal slide distance as we've laid out there. So indicate quantities that could be measured by the students that would allow them to determine that. If you're writing so briefly describe a method to reduce experimental uncertainty. In this case, we've got that set up. I would say, in fact, you can read the actual sample one that I have on there. I said, raise the block up to 50 centimeters vertical height, release it, let it slide down, and measure how far it slides before coming to a stop from the base of the ramp. That's my H and my D. Then I said, do that twice more and average the slide distance so that we can reduce experimental uncertainty. I do recommend when you tell me to repeat measurements to go through and tell me why we're doing it to reduce experimental uncertainty, to try and secure that other point. Then I also said, do it from 50 centimeters, then repeat those steps for 100 centimeters, then 150, then 200. I don't know if they're actually paying close attention on this. I'll have a better idea as we move forward with the redesign, but they've instructed you that you need to generate a graph. So your experimental procedure should get enough information that if you kept dropping this from a vertical height of 50 centimeters and you just did that 10 times, then you would end up with a bunch of dots right in here where this is 50 centimeters. You can't actually get a trend off of that. And if you average all of them, you end up with just one dot. In this case, you would have to have an experiment that goes to 100, 150, and then we'd have a dot like this and a dot like this. You have to have these spread out if you're actually making a graph. So that's another thing that you might keep an eye out for. As of now, I've not seen in the grading rubric that that's specifically something they're looking for, but I really think it is. And if it's not, it honestly should be, because that's how you design a good lab. Many of the labs on my website and for my class have been designed using exactly this method, thinking through, okay, what things can we measure and how to approach it. For part B, indicate what quantities the students could graph on the horizontal and vertical axes. Tell us explicitly. The vertical axis should be this value, vertical release height. The horizontal axis should be the slide distance. Be very specific on that and tell me what goes on what axis. And then clearly state which quantity will be graphed on each axis. The second point is briefly describe the relationship between mu k and the feature of the graph. In other words, this is where you tell us how you would read the graph to get mu k. In this case, if you do the vertical release height and the slide distance, I've now demonstrated to you with that proof that you could turn around and say, hey, when you graph that, the slope of your line is equal to your coefficient of kinetic friction. So, since they say briefly describe, they're not asking you to derive or prove anything on that, but you might give us, the grader, a little bit of an idea if you have the time. Say, I used work energy theorem and found that the total gravitational potential energy gets consumed or taken out of the system by the force of friction. And when you work with that, we find that by graphing the vertical release height as a function of the slide distance, our slope would be equal to mu sub k. I don't think you have to do that, but if you have the time, it makes a really good effect to show that you know what you're talking about. And you might be able to get some partial credit depending on how the grading rubric is listed. Let's see, this one's definitely going to be a bit longer of a video, mainly because the experimental design questions have a lot more open-endedness to them, and they're usually some of the more complex ones. The following information applies to parts C and D. In a different experiment, the students release a block from rest on a rough ramp. The block is released a distance d from a photo gate. The ramp is inclined at an angle theta above the horizontal as shown in figure 2. The block slides down the ramp and passes through the photo gate, which is positioned near the bottom of the ramp. The photo gate determines the speed v of the block as it passes through the photo gate. The unknown coefficient of kinetic friction between the block and the ramp is mu sub k. So they have a similar but different experiment. In this one, they're not measuring the actual heights, the vertical heights. We're looking at it from a kinetic energy viewpoint. Okay, the experiment is repeated several times with different release distances d for the same block. Table 1 shows the measured values of d and v. Pardon me. The students correctly determined that the relationship between d and v is given by this unpleasant looking equation. Don't panic. Here's one of the nice things. For AP1, they've fallen into the habit of giving you the actual equation so you don't have to derive it yourself. For those of you watching this in preparation of the APC exam, they usually don't give you this and you're going to have to derive this yourself. I'm going to, at the end of this video, try and go through and do a quick derivation of this so that everyone can see where this equation comes from. But for AP Physics 1, there's a good bet that they'll actually give you the relationship so you don't actually have to do that. They're helping you out, but you do have to know how to work with it. They also say, we have this expression, but they told us that theta is going to be equal to 30 degrees, and g is going to be near the surface of the Earth, so we would treat it as 10. The students want to determine mu sub k. The students create a graph with d plotted on the horizontal axis. What should we put on the vertical axis? So we need to put the quantity and units if appropriate. Make certain you put both on there. Looks like they've adopted this now. I'm going to try and incorporate this for the future. Quantity here and units if appropriate. Remember, not everything would have units, like if you had coefficients of friction or a couple of other things, they have no units that go along with them. But many of the things very well might. Okay, so on this, we've got the following. Going back to the same thing that I introduced just a moment ago, we end up with a straight line if we have y equals mx. So with this, they told us v squared equals the quantity of 2g times, I believe it was, sine theta minus mu sub k cosine theta times, I think that's all of it. Let me double check though. 2g sine theta, yeah, there we go. Times d, our slide distance. Okay, here's y, because it's on the opposite side. Here's x. They told us outright, here's d is put on the horizontal axis. So our smart money's on, this isn't the only thing that you could do, at least I don't think, but I would just put v squared over there. And that sets us up that this whole messy thing is my slope. Now, that's actually still going to be the easiest approach, doing v squared versus d. This is how we work with this, and this is how I work with my students to try and get them prepared for it. Y equals mx is your key idea. So whatever's on the far side of the equal sign, that's what goes on your vertical axis. We have this on our horizontal, and that would leave this for our slope. They set up that we would have d there. Okay, now that we've got that, I would go through, I'm going to save a little bit of time on this, and I'm going to jump over to my grading rubric on it where I filled this in. But the first thing that I would do, okay, now I know that I want v squared here, and my units would be, well, meters squared per second squared. And I would fill that in, and then I would see what numbers I'm actually dealing with. So on this, I would do the following. 0.29, I need to square that, so 0.29 squared gives me 0.0841. I would make another column out here, v squared, meters squared per second squared, 0.084, and then 0.38 squared. I basically fill these values in. And then once I have those, I would use those to see what spacing I need to do on this graph. I've already done that, so I'm going to jump straight to my grading rubric on this. And also you'll see that I'm using my color coding here, and I give a brief description of what we already went through. Here we go. On my graph, I'm going to jump down to what it looks like here. So we've got v squared, meters squared per second squared. I've got it. I went ahead and marked it here too, even though this should be appropriate marking on it. And then I saw the following. So here's what my table would look like. 0.084, 0.144, 0.17, 0.24, and about 0.27. So I would see that this goes from 0 to about 0.3. And I know that I've got 1, 2, 3, 4, 5, 6. So multiples of 3 should be easy enough. I did 0.3 maxing this out, then 0.2 here, 0.1, and 0, 0. And then here is what I'm putting on my vertical axis. Here's what I'm putting on my horizontal axis. Oh, it auto-capitalized that to capital D. It should be lowercase d. But here's one of my dots. Here's another, and I plotted the dots correctly with where they're supposed to go. Then I got out my ruler, and I did a best fit line. Now my circles here at the end are the ones that I'm giving a clear indication to the grader where I'm getting my slope from. I don't know if this is as important as it used to be, but this was a common thing on the APC mechanics exam for decades. And one of the key points was always tied to students using points on their line, not necessarily data points. So if you, on the old exam, if you found your slope using this data point, you'd be throwing away points for your exam. I'm still teaching my students to focus on give a clear indication to the grader where you're getting your slope from. In this case, I heavily recommend circles instead of dots. If you put a dot, it's hard for the grader to know if that's one of your data points or not. Make it easy on the grader to get you the points that you earned. So these are a few things that we've gone through in my class, and I want to reiterate here or share with others that I think would be a good approach on it. For most of the grading rubrics that I've seen, they're not looking specifically for you using points that are on the best fit line, but that is still 100% a good thing to do. Remember, none of your measurements are perfect. Any of these dots can be slightly off. This line represents the truth behind our messy measurements, and that's why we are prioritizing the line. Look for any spot that is easy to read. So this one was on a major unit here, and a pretty easy unit to read here. Same thing for this one and that one. So with this, apparently there are students walking by outside. I went through and I did my slope based off of, this one has a location of 0.44 horizontally, and that's in meters, and 0.2 vertically, and then this one is 0.1 meters and 0.04 vertically. So with those, I've got that marked here, 0.2 minus 0.04 with meters squared per second squared. This is my rise over my run of 0.44 minus 1.0, 0.44. Great. When I evaluate that to find my slope, I have 0.471 meter per second squared, or what my units come out to. Here's where it gets a little bit tricky. My slope is not magically the thing I'm looking for. How do I know what to do with it? Well, I have this as my slope, and I want to find mu sub k. So I found that my slope was 0.471 with appropriate units. I'm going to set that equal to 2g times sine of theta minus mu sub k times cosine of theta, and solve. Okay, well with this, here's where we got to remember that they gave us some numbers. 2 times 10 times sine of 30 degrees, and I can plug that into my calculator, minus mu sub k times cosine of 30 degrees. In this case, I've got an equation with a bunch of numbers, and the only thing I do not know is mu sub k. In my grading rubric, once again linked down below, hopefully, I solve for it, and then when you go through and actually finish solving, I got that mu sub k should come up to about 0.550. No units. I would remind you, if there are units on a numerical answer, always put the units, but because this is a coefficient of friction, it has no units. So here is how we do that analysis. Now, this has pretty normally set up locked in kind of points. You'll see this pretty often if you look at the experimental design questions. We've got the first point in section C when you're doing what I would say is the graphing and linearizing. For listing quantity, a quantity that could be plotted on the vertical axis to produce a linear graph whose slope can be used to determine the coefficient of friction. I went with v squared. You could have also divided it and had by 2g and had v squared divided by 2g. You would have had to do more calculations, and it probably would have resulted in more work, but that's another thing that could be a correct answer. So don't think that there's only one thing that you can put on the vertical axis. There's usually a couple of different things, but that doesn't mean that everything gets credit. C, for labeling the vertical axis correctly, including units, with a linear scale. I have students every so often that go 0, 1, 2, 17, 344. You need it to be a linear scale, so you need to space things out appropriately. That are spread over, I added the spread over at least half of the horizontal and vertical axes. They probably dropped that from the AP1 because they've actually filled in, and they know that your data points are being forced to be spread out over a decent amount of the graph. For APC, they may actually have it where you have to fill in both of the axes on this, and it will be important that you not squish your graph into the corner. So make certain that you spread it out. I went ahead and included this in there to remind students of that. The other point, for plotting data points consistent with one of the following: the quantities that you laid out in CI, the quantities indicated on your actual graph axis, or just the quantities that are given in table 2. So again, advice that I have for students: if you don't know what else to graph, just graph the data that you are given. You can still get quite a few of the points even with that. Hopefully you're able to do the linearization, but not necessarily guaranteed. So this is a nice way to back that up and at least still be able to get a number of points. If you just graph the data that's given to you, you will not get CI, the first point here, but you can get the second point and the third point, And the fourth point for drawing an appropriate best fit line that approximates the data. I remind my students that unless you know that it's linear, if you see a distinct curve to it, draw a curved line. We're looking for you to best match that data. If you're convinced that it is going to be linear, then definitely use your ruler. Again, the chief reader has told us to emphasize using a ruler. Okay, here was my example on that. The last 2 points. The first one is for correctly relating the slope of your best fit line to the value of mu sub k. So that was that part where we identified that our slope would be equal to, I'm getting ahead of myself. Slope, I've got it even color-coded here, v squared equals that mess of stuff, here's my slope, d, and so I've written specifically that I've got that mess of stuff equals what I found as my slope. Try and make that clear to the grader what you're doing. And then finally, the last point is for getting a correct value. In other words, being able to finish all the math and finish it all up and getting it as 0.0550 for this, or a correct answer in a given range. AP determines the range. I do not know how they do that. I'm estimating it for this one to be between 0.5 and 0.6. This usually requires units, but the coefficient of friction has none, so there aren't any units on this one. I'm going to stop here and we're going to pick up in just a moment. I will do a derivation to show you where this equation comes from, though you didn't have to do that on AP1, you might on other exams.